Good morning, good day, and good evening to all our attendees joining us for today's latest Data Science Central webinar. I'd like to start our event off today by thanking Pivotal for sponsoring today's event. This will be Pivotal's fourth educational webinar as part of a series this year in partnership with Data Science Central, also known as the Pivotal Data Labs webinar series. Pivotal is a wonderful partner and supporter of the Data Science Central community, and we are honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show some of our appreciation for other recent sponsors, including Cisco, Hortonworks, Tableau, Teradata, Splunk, and TIBCO, to name just a few. These past webinars are available on demand at datasciencecentral.com, and if you have not had the opportunity to view them, I would encourage you to take a look, as they do provide some very useful information. Today's webinar is entitled Using Data Science Techniques for Automatic Clustering of IT Infrastructure Alerts. And before we begin, I'd like to briefly review the format of today's webinar. Today's event will be approximately 1 hour long. We have a single panelist that I'll introduce to all of you in just a few moments. We should have about 10 to 15 minutes for Q&A following the presentation. And as always, this event will be taped and made available later on this afternoon at datasciencecentral.com. I'd also like to encourage our attendees to provide questions throughout the presentation. We will be reviewing them and presenting them on your behalf during the Q&A portion of today's webinar. My name is Tim Madison. I'm one of the co-founders of Data Science Central, and I will be your host for today's event. I'm very pleased to introduce today's panelist, Regu Radhakrishnan of Pivotal. Regu is a principal data scientist within the data science team at Pivotal, where he helps customers drive business value from data with a special focus on IT security, operations, and fraud detection. His research interests include statistical machine learning, video summarization, multimedia content identification, watermarking, and spatial audio. He has published several conference papers as well as 7 journal papers and a book on multimedia content analysis and security. He received his Master's of Science and PhD degrees in electrical engineering from Polytechnic University in Brooklyn, New York. Welcome and thanks for being with us this morning, Regu. We're looking forward to your presentation. IT departments within large organizations struggle with a common problem. An infrastructure that supports business-critical applications generates thousands of alerts per day that report on the health of various critical components. It's a very labor-intensive and expensive system to analyze all of these alerts and incidences to extract the information that is needed. In today's webinar, Regu will present the framework that was used to develop an automatic clustering alert system used in conjunction with Pivotal Greenplum Database, and draws approaches from graph theory and hierarchical clustering to help IT departments understand and process this data to improve their overall efficiency within their departments. So with that, Regu, I'm going to pass this over to you, and you can begin your presentation as soon as you're ready to go.
Thank you, Tim, for the introduction, and thanks for everyone for joining this call. I'd also like to take this opportunity to thank Data Science Central for this opportunity to present our work here today. This morning we'll look at how data science can help IT operations improve their operational efficiency, and this is joint work with my colleagues in the data science team at Pivotal. And I would like to take this opportunity to acknowledge Derek Lin, Jin Yu, Rashmi Regu, and Vivek Ramamurthy for all their contributions to this work. So here is the agenda for this morning. I'll first introduce you to Pivotal at a high level and our group within the Pivotal called Pivotal Data Labs. And then we'll go over some background on what are the typical IT operation data sources that you encounter, and some of the problems that are faced by IT operations folks and how data science can help address those problems. Then we'll look into the nuts and bolts of the actual clustering method that we developed for clustering these IT alerts, and then end with some results and discussion around what data science tools we use to accomplish this task. Pivotal as a company was spun out in April 2013 by combining big data assets from Greenplum and cloud assets from VMware. Pivotal's mission is to enable enterprises build data-driven apps in an agile manner that are backed by analytic insights. So that's the mission of Pivotal. And let's look at the diagram in the next slide, which gives you an idea about the cycle of continuous value creation that is driven by the relationship between apps, data, and analytics. My favorite example here is that of Netflix app, which people use for watching movies and rating them. All that data that comes out of this app is basically collected by Netflix to basically build a machine learning model, a recommendation system that can predict what movies you might like in the future. And this basically drives business value for Netflix. So you can think of it like this. Apps basically power businesses, and those apps generate data. And from that data, you can derive analytic insights to drive new app functionality. And the faster an organization can go around this cycle of innovation, the faster it can pull away from competition and differentiate itself. Pivotal is basically positioned well with its wide range of products and services that map to this cycle very well, and it lets organizations to basically store everything in a data lake, data from multiple lines of businesses, and run analytics on those stored data sets inside the data lake using analytic libraries such as MADlib, and that is available on top of the Greenplum database and Pivotal Hawk. And from those insights, build the right app for driving business value for our customers and deploy them in a scalable manner using Cloud Foundry. Here is another look at our portfolio of products and services. Here I would like to point out that the data fabric includes big data products, including Pivotal HD, Greenplum Database for the MPP analytics, and Hawk, which is a SQL engine on top of Hadoop, and Gemfire, which is an in-memory database for handling high-volume transactions. And the app fabric includes products such as RabbitMQ, Tomcat Server, and things like that. So both the app fabric and the data fabric are sitting on top of Cloud Foundry, which you can think of as the new operating system that is on top of an underlying cloud infrastructure, be it Amazon or OpenStack or VMware, or it could be even the on-premise cloud of an enterprise. This Cloud Foundry basically enables enterprises to be cloud agnostic, and on top of all these products, we have two service-centric service delivery organizations, and Pivotal Data Labs is one of them. I'm basically from this Pivotal Data Labs organization. It is a group of data scientists and data engineers who help customers derive value from data that is stored on Pivotal Stack. So in order to help our customers, we have multiple package services ranging from a 2-week lab primer to a in-depth 12-week data science lab. In a lab primer, we basically work with customers to understand what data sources they have and come up with a prioritized list of data science use cases that they could execute on in collaboration with their stakeholders. In a data science lab, we take a specific business problem and work on it for 12 weeks and deliver a data science solution with a code-based framework and ready to deploy model for them to operationalize in their environment. So the subject of today's talk is actually one such engagement with an IT operations department within a large financial organization. So let's look at the background on some of the IT operations data sources and the problems that they face day to day, and see how data science can help within that framework. Traditionally, IT operations was seen in a supporting role. They were doing payroll automation, business process automation, and things like that. More recently, the trend is to basically leverage IT operations to improve operational efficiency and gain business advantage. Many large organizations are looking to play in this space as well. The problem is this: the enterprise network is very complex. It has various components such as servers, storage, network devices, middleware, and all of these technology components have a lot of dependency between them. And the role of reliability engineering within the IT operations is to make sure that business critical applications are running all the time 24/7. And in order to do that, they need to be monitoring the alerts that are coming out of each of these technology components, reporting about their health. And if there is some issue that needs to be fixed, then they need to quickly resolve it to ensure the strict SLAs they are under with. So given this problem and the volume of data, it's very labor intensive and expensive to do all this work manually. So where there is data, it's natural to ask how data science can help to improve the operational efficiency of IT operations. So let's take another look at the infrastructure. We basically have business services such as debit processing or fraud detection. There may be multiple business services that are running on top of the IT infrastructure, including components from network devices, storage, servers, and middleware components. Like I mentioned earlier, all these components are generating alerts about their own health, and these alerts are machine-generated data, so you can think of them as semi-structured text. And all this text gets fed into a rules-based engine, and that rules-based engine is going to bubble up critical issues to operations support personnel, which are people who are looking at monitors to see what issues need to be raised as incidents so that they can be fixed. So they create incident tickets out of some of the critical alerts that needs to be fixed, and sometimes the incidents may also be manually created, like when a customer calls in to report a problem that some service is down. So given all that data, basically we have three types of data. We have the alerts, which is semi-structured text, and then we have manually created incidents, which is unstructured text, and then the incident work info, which captures information about what was done to fix a particular problem. Given all this data, there are multiple opportunities for data science here to help improve the IT operations. The first problem we could be looking at is what are the typical failure patterns in the IT infrastructure. Basically, you're interested in the top 20 incidents that keeps the operation support busy, so they can look at these top 20 issues and try to fix them and then keep improving their operations. The second problem is, given an incident that has occurred and historical data, can we recommend a set of resolutions automatically? For example, if incident A that is coming in is similar to incident B in the past, maybe the steps that were taken to resolve incident B in the past still applies for A. So that's where machine learning comes in, right? You take the historical data and understand if this incoming incident A is similar to some incident in the past, so you can recommend resolutions. Problem 3 is the ultimate goal of IT operations, to be able to predict failures before they can occur. This involves root cause analysis and looking at component-wise logs to actually predict failures before they can occur. So as you can see, there are multiple opportunities for data science here. The focus of today's talk is just problem 1. We are going to just look at understanding all these alerts that are coming in and day out, and looking at that volume of alerts and seeing what are the top incidents or issues that keep my operations support busy. Before we get into the actual clustering framework, I'd like to touch upon some challenges here. The challenges are twofold. From the data front, you have a large volume of data to handle. For just one business service, to give you an example, in just 6 months, it can create about 10 million alerts. And all this data can be semi-structured and unstructured, and there is no labeled data to start with. From the analytics front, because the alerts text are coming from machine-generated data, they are they are basically short descriptions of the issue, and you cannot just apply some document clustering work from literature and hope that it would work. So we need to be developing a clustering technique that would work for this scale and this type of data. And finally, it's not sufficient just to generate the clusters. We should be able to visualize the clusters so that we can get feedback from the subject matter experts and iterate on the actual clustering algorithm and improve our results. These were some challenges that we had to deal with. So now let's go into the actual clustering procedure itself. It has these 5 high-level steps. The first step is token normalization, followed by stop word removal, and then we will we'll define a distance metric to compare any 2 alerts and compute pairwise distance between all the alerts. And once we have computed the distance, then we'll be able to apply a graph theoretic approach to cluster all these alerts, and then we'll post-process these alerts, visualize them, and then go around this framework a couple of times to settle on the type of clustering we like. I'll go into each of these steps in detail in the coming slides. Step 1 is the token normalization. Recall that basically alerts include some specific dates and IP addresses. For example, it might say server with a certain IP address is not responding. And there may be another alert which says server with a different IP address is not responding. As far as we are concerned, both of these alerts point to the same issue, but they appear different because of the specific IP address in that field. So what we are basically doing with this approach is that replacing some strings that are not valuable for that are not important for clustering with the standard strings. For example, the dates and times will be replaced by just the string date and time. The file paths, URL, server names, and IP addresses, they have to be taken care of. So after this step, we can bring down the number of unique alerts from say 500,000 to 22,000, which is more manageable. This is an important step. This is already providing some level of clustering. And we also had some metadata associated with each alert, which said whether it was a Windows Server related issue or a Unix Server related issue or a database related issue or a network related issue. So basically we have now grouped the alerts into 4 different buckets, and now we have to just look at finding clusters within each of these alert groups. So the problem has been broken down into 4 smaller sub-problems. Then we need to remove stop words. Stop words are basically common words that occur across all the alerts, like the word the, is, or has. They occur in all of the alerts, and they are not going to help you towards clustering. So in order to identify these stop words, we basically do a word count histogram within each alert group and pick the top K words as stop words and remove them. The next step is to compute pairwise distance between the alerts. And you can first represent each alert as a bag of words. By this, we are ignoring the structure within each alert. We basically consider each alert as a bag of words. So the order of the words doesn't matter. So given two sets of words, A and B, corresponding to two alerts, A and B, we can compute distance metric called Jacquard distance, which is defined as 1 minus the cardinality of the intersection between the two alerts divided by the union, cardinality of the union between the two alerts. So for example, if alert A says server X not responding and alert B says server Y not responding, the Jacquard distance for this, for comparing these two alerts, is basically 1 minus the number of distinct words in the intersection, which is 3, divided by the union, number of elements in the union of these two sets, which is 5. Jacquard distance is always a number between 0 and 1. So if the intersection between two elements, two alerts is 0, then you have the maximum distance, which is 1. We also played with other distance metrics, but this worked with and settled on this particular distance metric. So once we are able to compute the pairwise distance between all the alerts, then you can build a graph where the vertices of the graph correspond to the alerts themselves, and you draw an edge between two vertices or two alerts only if the distance between those two vertices is small enough. So you use a threshold to decide whether you would connect any two alerts. And once you have this graph, you can run a standard graph algorithm called connected components on this graph to basically identify the clusters. A connected component is basically, you can think of it as a subgraph that is not connected to any other part of the graph. So it will automatically find clusters, and the nice thing about this connected components is that the cluster shape doesn't matter. As long as you're able to find a subgraph that's not connected to anything else, then you're good to go. But there is a problem with this approach, which I will mention in the next slide. So just to recap, we started off with the affinity matrix or the distance matrix, which is basically the n by n pairwise distance matrix between the alerts, and we used a distance threshold to create a graph, and then we ran the connected components detection algorithm on that graph to identify clusters. But sometimes the connected components detection algorithm gives out large connected components, and those subgraphs are difficult to interpret because they may have multiple types of alerts within those, and so we had to use another graph partitioning algorithm to basically refine the clusters. So it will become clear in the next slide what I'm trying to point you to. So on this slide, I'm showing the cluster IDs on the x-axis and the size of the clusters on the y-axis. You can notice that it has a long tail distribution in terms of number of clusters, and there are a few big to medium clusters. The first cluster is about 1700 alerts in size, and we basically need to break this down further using the graph partitioning algorithm that I will go over in the next slide. This is the graph of the largest connected component, which had 1717 normalized alerts, and you can see that on the bottom left corner, basically this is an affinity matrix where each element in this matrix is the affinity between or similarity between any two alerts I and j. So you can see in the bottom left corner of the picture that there is a group of alerts that are very similar within themselves but less similar to the rest of the alerts. So you could break this large connected component into further meaningful smaller clusters. So that's what this graph partitioning algorithm does. So you start with the affinity matrix or the distance matrix from the largest connected component, W, And then by solving an eigenvalue problem, which is well known in graph partitioning literature, it's called Normalized Cut, and it provides you two partitions A and B from this large graph, and we compute the homogeneity and size of the two partitions A and B, and check if we further need to partition this. Basically, we look at how similar are the clusters in these partitions A and B to the centroid, and then we look at how many alerts are there in each of these partitions A and B. And if you are not satisfied with the homogeneity of the cluster, we further decide to partition these two smaller partitions A and B, and go until we satisfy the criteria. That's why this approach is also called hierarchical top-down clustering, because you start with one cluster and you hierarchically go down and create more clusters based on the stopping criteria. So we did that for that first large connected component, which had 17 alerts, and we ended up with 4 smaller clusters that are more manageable, and they satisfied the criteria for homogeneity and size in terms of number of alerts within each group. Now let's look at the results from all this clustering work that we did. For each of the alert groups, you can see a Tableau visualization of the size of the clusters in each of the alert groups. Each color, the red color is pointing to alerts from the Windows Server issues, and then the blue one is from the Unix Server issues. And the size of the bubble in this plot is basically pointing to the volume of the alerts. And you can also see that there is a long tail behavior here, because there are a few large to medium clusters, and then there are a lot of small clusters. But for improving IT operations efficiency, we only need to look at the big to medium clusters and derive meaningful performance indicators to basically learn from these clustering. So in this slide, I'm showing a particular metric that we derived from each of the clusters. It is called the mean time to resolve. For each alert, we can compute the time it took to resolve that incident. And by computing the average in a cluster, we can compute this metric called MTTR, which is a key metric. By looking at this, people in the IT operations know that these are all my top issues, and this is how much time we are spending towards fixing each of these alerts. So by looking at these metrics for every week, they may prioritize how things need to be fixed. Certain issues may be handled by a different solution, and that issue may go away in future. For example, you may also look at trends of number of alerts that are occurring over time. So let's say you rolled in a fix for a particular issue, and you expect to see that in future there should be less and less of those issues occurring if the fix was correct. So you can look at different types of things that you can learn from this type of analysis. We also developed a cluster visualization technique, which was key in our work, because like I mentioned earlier, we had to go around the framework we had to iterate on the framework for multiple iterations until we settled on a particular clustering that was acceptable for the subject matter experts. Typically, when we visualize clusters, if we just did a word cloud, which basically is based on how many words are occurring in what frequency within each cluster, if we actually display that word cloud, then it's very hard for the subject matter expert to make a prediction, understand whether the cluster is homogeneous, and understand the text structure within that alert. So we came up with this alternative cluster visualization where we preserve the structure of the alert itself. So for example, on the leftmost part of the figure, you are looking at the word position as token ID going from 0 to 22, and then on the x-axis you are seeing how many percentage of the words, how many percentage of the time the word occurred in that position. So by reading off the entry, the words in the rightmost in the red circle, you basically get an idea of what this cluster is all about. For example, the second cluster is talking about something positive, alert, harmless, and these positive, alert, and harmless tend to occur in the same position in all of the cluster members. And then the similar interpretation can be performed for the third cluster here. So with this type of visualization, we were able to receive, we were able to show the homogeneity of the cluster, and it was easy for the subject matter experts to interpret what that cluster contains as prototype. If we just did a word cloud, they don't get an idea of what the particular cluster consists of. Now let's talk about how this framework can be operationalized. We basically first perform the clustering operation on a 3 to 6 month window of data, like we did in this case. And then for every day, as the alerts are coming in, you are going to assign the incoming alerts one of these clusters based on distance metric that you compute to the centroid of each of these clusters. If the distance to any of those centroids don't match, then you put this incoming alert into a new bucket. So you can also find emerging patterns as you go along. And you monitor the cluster statistics or other key performance indicators and trends on a dashboard that correspond to these clusters. Then every now and then, we basically need to perform this clustering operation to make sure the clusters are relevant as we go along in time. Now let's talk about the different data science tools that we used in our framework to accomplish this. We performed all this work on top of Pivotal Greenplum Database, which has an MPP, massively parallel processing, shared nothing architecture, and it has a master node and a bunch of segment nodes that share the computational load, and it is built for big data analytics and scalable computation. And on top of GPDB, we also have this open source machine learning library called MADLib, which comes with built-in machine learning algorithms like popular machine learning algorithms like LDA, random forests, and SVMs. And basically, you're not limited to you're not only limited to all the algorithms that are available in MADLib. You can also implement your own algorithms on top of GPDB using PLR and PLPython. In our case, we had to implement GraphCut, which was not part of MADLib, and we were able to do that quickly. Similarly, the connected components was implemented using PL Python. And for visualization, we use Tableau, Gephi, and R in our work. So to conclude, the takeaways from today's talk is that data science, we showed that using data science we can improve IT operations efficiency. We have just scratched the surface here because we can do furthermore based on data science. We showed that by collecting all the alerts, you are able to first provide intelligence to IT operations folks to say what are the top 20 issues that are keeping them busy. And going forward, we'll be able to use historical incident resolution data to basically recommend resolution for an incoming incident automatically. And the ultimate goal for IT operations, data-driven IT operations, is to be able to perform root cause analysis and predict failures before they can occur using data science. And to do all this work, we need a big data analytics framework that is supported by an MTTR architecture like Pivotal Greenplum Database. And it also has the flexibility for you to implement whatever algorithm you need to innovate as you go along. So the framework, you already have some built-in functionality in MATLAB, but the Pivotal Greenplum Database is flexible enough for you to be able to write your own algorithms using PLR or PL Python. Also, in our work, we showed that cluster visualization is critical because we need to be able to quickly get feedback from the subject matter experts within the organization to actually tune the clustering results. And we actually did that in our work with this large financial organization. And for further details on the actual work, you can look at the KDD 2014 paper that we wrote on this exact work. And there is also a blog by my colleague Derek Lin on the same topic. So that concludes our presentation for today, and I'm open for questions now, and I'd like to pass it on to Tim.
Great, thank you, Regu. It's a great presentation. You did a wonderful job, and it's lots of very useful and helpful information, I think, to our audience out there. So questions have been coming in. Thank you to the audience. I'm going to start the Q&A in just a moment, but I want to make a quick announcement that you all can take down Regu's information here, his email address, and contact him directly if you have additional questions or want to reach out to him following today's event. So the first question I have for you, Regu, is does an agent need to be installed? Is one of the first ones we have for you.
That's a good question. So he's asking about how the alerts are being collected. So there is an alert management tool called IBM Netcool, which is an IBM product. And it is basically taking care of collecting all those alerts, and it lets you define what rules you may have to bubble up those alerts, what you consider as issues for your organization. So I do think there's some agents involved here.
Okay, very good. The next question is, in all the exercises, what is an actionable analytics visualization? This person seems to be a little skeptical on the operational benefit and is asking you to clarify.
So that's a good question as well. For example, let's go to slide 35, where I'm creating a visualization of the number of the top 20 issues that we identified as clusters, and then we were able to compute the mean time to resolve for each of those issues. For example, the first issue says there's a space utilization issue in many of the servers, and that issue takes most of the time to resolve. And so you can do something about fixing this issue by looking at what is happening with a particular issue and how long it is taking to resolve, and by looking at this visualization, people can prioritize their resources and focus on what needs to be done to keep the operations going on efficiently. Without this visualization, today they don't even know what are the top issues that their operation support are busy with. So this is just the first step in the right direction, but I agree that there's a lot more that can be done for actionable insights.
Okay, very good. A nice, thoughtful answer. Next question is, how does this clustering differ from MapReduce, and are they related?
MapReduce is basically for batch processing from the unstructured data, right? You have a bunch of logs and you're collecting information from those logs and creating structured data. So this clustering is not related to MapReduce in a direct way. It's an algorithm where you are bringing together alerts that have the same look and feel. So the several steps that I described are towards that. We first did the token normalization to bring alerts that look different, but we brought it down to smaller groups, and then we applied a bunch of distance computations where we were able to compare different alerts, and we are basically discovering the natural distribution in the data by doing this clustering operation. So MapReduce is like a design paradigm. You could implement all of this using MapReduce, but I haven't thought about that. So these are two different things.
Okay, very good. Our next question is, how did you assign the business meaning to the selected clusters?
That's a good question as well. So that goes back to the cluster visualization. So let me go back to slide 36. So for example, let's look at the third cluster, which is easier to look at. We basically collected all the alerts that fell into a particular cluster, and then saw how many times a word occurred in a particular position in that cluster. And in this case, AIX, hardware, and error always occurred in the first three places, and there were a lot of other things that followed it. So by showing this visualization to the subject matter experts, they basically put a label on that cluster saying, oh, I know this issue. This is because something is wrong with this hardware. And similarly, the first cluster here is talking about some Oracle exception that happened. And so you can basically, there needs to be manual intervention the first time you design this algorithm. Once you assign business meaning to each of these clusters, then you start to monitor what is happening with those groups of clusters over time. I hope that answers the question.
Yeah, that's a very thoughtful answer again. The next question for you is, will this framework work on unstructured text data? You showed an approach for semi-structured machine-generated alerts, so I think they want a little more detail on unstructured text data.
Yes, framework is similar in that there were the same 5 high-level steps: the token normalization, stopword removal. These are standard pre-processing text steps, and then we had to tweak a little bit for the distance metric, and also we had to use a KD tree. This is basically described in our paper. We did apply this similar framework, but with some tweaks for dealing with unstructured data. So the short answer is yes, it can apply. We can come up with a clustering method that's applicable for this unstructured data as well.
Okay, very good. And while we're on the clustering topic, what other clustering methods did you try?
We tried a bottom-up clustering method, which starts off with each alert being in its own group, and then using a distance metric, you start to combine groups that are closer in distance, and build a tree, dendrogram tree, and then you cut that dendrogram at various levels. So that's another standard approach for bottom-up hierarchical clustering. We tried that approach as well, but we found that it produced too many clusters, and it was hard for the subject matter experts to pinpoint which clusters were relevant. So we went with a top-down approach where we started off with a smaller number of clusters, and then we broke the clusters down until we found some homogeneity within the clusters, and they only cared about the big to medium clusters.
Okay, very good. So the next question, again, sort of in the same topic here is, so can we analyze our current HP monitoring events with your product based on clustering timeframe?
So the HP, I'm not familiar with the HP monitoring event, so I'm assuming it's going to generate some machine-generated log. If that is the case, then we will be able to look at that data and apply the same approach. Actually, we were able to replicate this work for a similar product within Greenplum. The Greenplum basically sells DCAs, the data computing appliances, which were reporting back dial home alerts, which is also semi-structured data, and we took the same all the data from multiple customers and did the same clustering algorithm and found the top 20 issues that this device is causing problems for out there in the field. So I'm imagining it's a similar scenario here. So for whatever equipment you are trying to learn about, we can collect all the text data and perform the same approach again, I think.
Okay, and that may be a good question for the attendee to connect with you offline after the event as well. The next question is, I think they're looking to get a little information in terms of the scalability of the product. So does the organization or the enterprise IT need to be a certain size for this to be implemented, or can it be scaled proportionally?
Can be scaled proportionally. So the question is about whether the data it has to be a large volume, or it can handle. Mm-hmm.
I think more in terms of how large the enterprise IT should be for this to be a reasonable application. Does that help?
Yes. Yeah, the method itself is applicable to any type of data. So like I mentioned in the previous example, right? We were only looking at a particular product that was sending out dial home alerts, and we were able to apply this approach there, and it was found valuable for the product team to understand what are the issues for that particular device. Of course, if you apply it to the whole IT infrastructure, then you get the benefits accordingly, right?
Okay, very good. Regu, can you go into some detail on how you went about validating the cluster results?
Yes. Let me look for the corresponding slide. So recall that we were we were dividing the problem into 4 subgroups, subproblems. Basically, we looked at Windows Server related issues, Unix Server related issues, and database related issues. And after one round of clustering, let's say, we basically looked at the homogeneity of each of the clusters. So you can measure how similar the alerts are within a group to the centroid. So we can compute a measure called cluster radius, which tells you how homogeneous the cluster is. And we also showed these homogeneous clusters to the subject matter experts to tell us whether those issues need to be in the same bucket. And so by looking at both of these metrics, we were able to settle on a set of groups that work for them. So I see the point in his question in that since it generates a lot of clusters, it's very hard to look at all of those. But in order to improve operational efficiency, you only need to be looking at the big to medium clusters. There will always be a lot of small clusters that don't impact your operations, right? So you only need to be looking at the big issues that consume your resources. So that's the approach we took, actually.
Okay, very good. And there's an appropriate question that just came in while we're on this slide. What is the cutoff for homogeneity in the cluster, and will it depend on the input data size?
The cluster measure, the homogeneity measure, is also a measure that's well known in the clustering literature. Like you compare each of the elements in the cluster to the centroid, and that distance is a number between 0 to 1, and you need to choose a threshold carefully. That depends on the data, so you just have to play with it. I don't have a hard number on that.
Okay, no problem. Next question, Regu, is do you have any recommendations regarding partitioning of data before applying analytics? For example, analyzing infrastructure events separate from application events.
So if the data lends itself to partitioning, we should certainly do that. That will basically bring down the volume of data that you need to be considering. For example, if you are worried about creating a dashboard for a particular business service, let's say debit processing or fraud detection, then you need to look at all the dependent infrastructure components that may cause that particular business critical application to fail, and look at only that partition to be able to be meaningful. If you do it that way, then it's meaningful for that particular business application. If you just did partitioning of the data, let's say you said I'm only going to look at network device related alerts, then it's only useful to that extent, right? You only know that it doesn't give you the visibility into what business applications it's affecting.
Okay, very good. And Regu, while we're on, again, this slide, one of the questions is, can you go into some detail in terms of how you went about creating the cluster visualization? I think you mentioned it was using Tableau, but perhaps you can explain the visualization component of this and how it's integrated.
So we basically created the clusters in the Greenplum database, and we have the connection from the Greenplum database to Tableau, and Tableau has this nice bubble plots which you can plot, where each cluster has cluster radius and the volume of alerts that corresponds to each of the clusters, and you also have a prototype description of each of those clusters, and you can use all of this information to create this visualization on an ongoing basis. And you can also create other visualizations where you're monitoring how many alerts in a particular day is falling into each of these buckets, and then you can look at trends as well. So I'm not showing all those visualizations here though.
Okay, so they have other options as well within the product, it sounds like.
Yes.
Okay, great. So Regu, the next question is, can you go into some detail about the volume of data that you worked with?
So we started off with looking at just one business service, one business application, and then the components that were related to that. And it was about 6 months worth of data, and it boiled down to about 10 million alerts in the raw data itself. And then by doing some data munging and filtering out unnecessary events, we were down to about 500,000 alerts, which were unique for that 6-month period. And from there, by doing this token normalization step and then dividing the sub-problem into, dividing the main problem into 4 sub-problems, it further went down. So you can think of it like a funnel. We had a lot of data in the beginning. By data munging, we were reducing it to smaller and smaller groups, and when we finally applied the clustering method, I think it could have been run in a single machine setup. But to get to that point, you need the big data framework.
Amazing. Okay, the next question is, is this framework ready for real-time incident data management, analytics, and clustering?
Yes. Basically, we delivered this work to our customer, who is a large financial organization. All they had to do was, we delivered this code-based framework. All they had to do was take these buckets that were defined by these clusters, and then we could just basically assign the incoming clusters to one of these already identified buckets, and then derive metrics on each of those events over time and show it in a dashboard. It can be easily consumed by the IT operations folks.
Okay, excellent. Another question is, how did you evaluate the various data science techniques before sort of zeroing in on or selecting the ones that you felt were the right ones?
Yes, that's also a very good question. We had competing approaches, like I mentioned earlier, the bottom-up hierarchical clustering approach, which did not use any graph theory. We also played with different distance metrics. For example, we chose checkout distance, but we also played with another distance metric which paid attention to the order in which the words appear in an alert. The checkout distance is just a bag of words, right? So you don't worry about the order of the words. So we played with different distance metrics as well as different clustering methods. And in the end, we settled on this based on manual feedback from the subject matter experts, and also we had to keep the number of clusters to a smaller number so that we can ask feedback from them, right? So it's a hard problem because you don't have any label data. It's hard to actually settle on an algorithm in an automatic fashion.
Okay, very good. So some wonderful questions, some very thoughtful and great answers, Regu. Unfortunately, we're just running out of time, so I want to make sure that those that have asked questions to rest assured that I'm going to send them all to Regu, and he will make sure that they are responded to directly. So again, thank you for some great participation. I just have a couple of quick announcements to make. To please mark your calendars for October 14th and our next Data Science Central webinar, Open Happiness Through Data Visualization and Business Intelligence, at Coca-Cola, sponsored by Tableau Software. Also, as I mentioned, our event today is being taped and will be made available later on this afternoon at Data Science Central. This brings our webinar to a close. I'd like to, again, thank Pivotal for their sponsorship, and a special thank you to Regu for his insight into today's topic. And we will look forward to seeing you all again at our next event on October 14th. Thank you very much and good day.